is basically modeling of overhead steel tank, and then we are about to create the first node. Let us assume that the steel tank is spaced at 2.5 meters center to center. We can copy and paste in the positive y direction. Let us assume 2.5 also. Now that we have these, we can create the columns geometry, connect beams along the y-axis. We can also collect the beams along x-axis and along the z-axis. Then we create the diagonals. Okay, having done that, we can go back to geometry, go to section database, we go to British sections, used for universal beams. Let's assign this section to be for the stanchions and also for the primary beams, and let this be for the secondary beams. And then we assign universal angle sections 50 by 50 by 4, and I'll let this be for the diagonals. So we can select the stanchions and say assign to selected beams. The horizontal members, we can select them and assign this to them, while for the diagonals, we can assign this to them. So the 3D of what we have done is something like this. On the contrary, you can go to label, structure. Let's look at the full sections so that we'll be able to appreciate it more. Having done this, we can take the translational repeat command to create the additional let's say additional 4 steps in the y direction, and of course the spacing will be 2.5. Make sure that you set all. Yeah, we've been able to get this. All right. Having obtained this, we can create the supports. Let's say pinned connection, and reassign to the supports. The next thing is to model the platform that will receive the tank load. We can say few selected objects only. We can define the primary beams. Now let us assume that the primary beams we cantilever out, let's say 800 mm. In the x direction, we can call this 0.8, and now in this direction minus 0.8. So okay, so this is what we have. We can as well join the members. Okay. After this, we can look at what we have done so far. We can look at what we have done, and okay, so we can create the secondary beams. The secondary beams will also cantilever 0.8 in this direction, so we can copy and paste, let's say in the z direction minus 0.8, and also in this direction positive 0.8. Alright, so we have this, and this. Now we will assume that this particular member is gonna be spaced at a distance. This is 4.1 meters, and okay, so let us space this at let us space it at a distance of 410 mm. We can highlight this, the beam members. We can do translational repeat. Now it's gonna be in the x direction. Let the number of steps be 9, and let the default spacing be 0.41. and let's see what we got. So we've been able to get it done, even though we will need one more step at this point. Yes, we've been able to get what we are looking for. So for this particular member, we have to also assign properties to it. We have some angle members here already, even though um we are actually not gonna need them. We're actually not gonna need them, but let's see what we can do. So if you selected objects only, so that we can delete these members that we do not need. Then if we return the full, then you discover that we no longer have the angles at the top. So we can assign the properties to the secondary beams geometry. We select beams parallel to the z-axis, and we can say view selected objects only. Then we can assign the universal beam section to it. Then we can view the whole section again. We can look at it differently. We need to assign properties to the primary beams also. You can say select beams parallel to the x-axis. View selected objects only. So the 3D of what we have is something like this. Which I believe you can appreciate. And more often than not, the secondary beams are usually resting on top of the primary beams. A simple way of doing that, of bringing the secondary beams on top of the primary beams, is by using the offset command. By so doing, you can get the secondary beams on top of the primary beams. Then also, by the time we mesh, you should be able to transfer the loads to the secondary beams, and then before it gets to the primary beams. So let's see how we can get that done. We go over to general, repeat in section so that you can have a good idea of the model we've created. The next thing that we should have done ideally is to mesh the plates, but let's attempt to get it done. Let us attempt to get that done, even though there will be need to do other things before then. Geometry. So we are just going to apply a template on this. Alternatively, we can avoid meshing, then transfer the loads from the plates as uniformly distributed load to the secondary beams. That's also an alternative that can be thought of. So we run our first mesh, say quadrilateral. In this direction, let's give it 3 divisions, and in this direction, let's give 12, such that this is gonna be constant all the way. Yeah, I thought as much. It's okay. It's okay. No. Let's give this 3. Let's give this 6. 3 and 6. Okay, it's a final mesh, but we give this 3. It can work. It can work. Give this 3, 6, 3 and 6. Alright, Okay, we have something like this. They're not too perfect, but when you're doing your own, you can mesh it in a more appropriate way. Okay, so we can assign a property to it. Let's say it's a plate that is 5 mm thick, and let the material be steel. You can add, take the cursor. Alright. If you watch, the mesh broke up both the primary and the secondary beams, which means if you should load it this way, load is gonna be transferred to both the primary beams and the secondary beams, and we don't want that. We want the load to go to the secondary beams, and then for the secondary beams to go to the primary beams. The most effective way of achieving that is to merge the secondary beams, the primary beams rather, at the points where the mesh have broken them. To achieve that, let's take a look at this again. We say view selected objects only. We return to this view. So we are gonna be merging the primary beams at these points where necessary. For instance, you take this point, okay, you come down here, merge, okay, say merge selected members. So if you watch, this now gonna behave as one unit. So we're just gonna do that one after the other. um just gonna do that. Okay, so we've been able to get that done. So whether we offset the secondary beams or not, we are gonna arrive at the same result. So generally, the modeling is complete. Um, the modeling of the structure is complete. So the next thing we can do is to apply the loads. You can say load and definition, say load case details. We add load case 1. Let us call it the self weights. We say add second load case. Let us say the weight of water with the tank, of course. And now let the third load case be for wind. Alright, so for self weights, we are gonna add the self weights in the negative y direction. We are gonna assign this load to the entire structure. So we take the geometry cursor that will capture both the plates and the beams. We say add, and then we have the weight of water. We are going to apply a uniform pressure load. Go to plate load in the global y direction, pressure on full plate of minus 25. We assume that this includes the self weight of the tank, and then for the wind load, we're not gonna stress ourselves. We've explained in our textbook how you can calculate wind load for such structures, but we will pick a nodal load in the y direction, going in the positive x direction. We can say 5 kilonewton. Then at the lower level we can say 4, even though I'm very sure it can't get up to that from experience. We can say 3, and then 2. Let's stop there. So this pressure load is gonna be on the plates. Alright, so we can say assign to selected plates. That's it. And now for the concentrated wind load is 5, 4, 3, 2. Okay, we know how we're gonna do that. We can change the view. This node, we need to get it exact. Okay, so at this intersection and at this intersection, we are assigning the nodal load of 5 kilonewton. Now at this point, we are assigning 4. At this point, at this level, we are assigning 3. At this level, we are assigning 2. And at this level also, we are assigning 2. So the loading is complete. We can define our combinations. Load case details, say add, define combinations. Let us consider just one load case here. Um, on your own, you can define other combinations. So the load case I'm considering here is um, dead load plus imposed. All right. We are talking about the self weight and then the weight of water. The self weight we are multiplying by a factor of 1.35, and the weight of water let's multiply by a factor of 1.5. Can say add. So once we are done with this, there are other actions that may come in effect of imperfection and all the rest of them. Um, we can you can apply those loads on your own by following the procedure described in the textbook. We can now go to analysis/print and say, oh, I would like the structure to perform buckling analysis. Let's say 10 iterations. We say add and then we close. When we go to the post print, define commands, let all the loads come in, then we say close. The structure has been successfully loaded, and then we can carry out the analysis. There is a warning. Let's check what it is all about. Okay, it's not a problem. Alright, so we can go to the post processing without wasting much time. You can see the deflated shape under the action of wind. Um, this is for the weight of water. You can see the deflated shape under the self weight. You can see then under the dead and imposed load. You can see. Remember that we didn't consider the effect of wind. Then it's an important um, uh, issue that you can also take a look at. You can view the moment diagram under dead and imposed load. You can see how the beams are deflecting, both the primary and the secondary beams. You can see the bending moment on the columns. You can go to graph, view them one by one. You can see that just like what we got, the axial force in compression 158 at this support. You can view the bending moment of about 9.5. You can also view you can see that the members are subjected to some little bending moment. You can view the value of the axial forces. So I believe you should be able to go through all the results. You can view the support reactions under the different load cases and all that. So by the time you are done with this, you should be able to obtain the internal forces that can enable you go through the design process. You can also view the internal stresses on the plate, even though it may not be too important for structures of this kind. Yeah, these internal stresses on the plate. So thank you very much for watching, and thank you so much for purchasing this video.